Today we're going to take a look at some demonstrations related to the concepts of pressure and buoyancy. We'll do some kind of qualitative demonstrations, and then we'll also gather some data to try to make some conclusions about buoyancy in particular. So I have kind of a note sheet that I will post a link to in the video description. We're going to kind of take some guided notes, take some observations, and work through those together. And that might be useful to have to kind of fill out as we go. So concept number one is that pressure in a fluid is caused by the cumulative force of gas or liquid particles on a surface. So when we talk about pressure, we're talking about fluids. A fluid could be a gas, a fluid could be a liquid. Definition of a fluid is a substance that flows, right? We know that's true of both liquids and gases. There's a really good simulation of this on the PAGT website that I'm going to bring up on the screen. So what this simulates is gas particles in motion. This is actually really zoomed in, so I don't know if you can see the scale, but it's 10 nanometers. So this would be a very small parcel of gas. And you can see the gas particles colliding with one another. They're in motion, but they're also hitting surfaces, right? So we think of pressure as being created by all of those cumulative interactions, little collisions, little bumps into the surface. And cumulatively, all those gas particles or liquid particles in the case of a liquid can exert a very measurable force, okay? So all together, we've got these many millions upon millions of collisions in a regular larger gas sample, and those collisions together exert a force. Now, when we measure pressure, what we're actually measuring is that force per unit area. And so if we are looking for a definition or a formula to calculate pressure, it's going to be the force per unit area. So the total force divided by the total area. Symbolically, we could call that capital F for force and capital A for area. Now, if we're working in physics, we're using our standard units, force is going to be measured in newtons, and length would be measured in meters. So when we look at area, it's going to be measured in square meters. So kind of our standard unit in physics for pressure is newtons per square meter. And that gets a special name. It's called a Pascal, named after Blaise Pascal, a mathematician and scientist who worked out some of these ideas. Symbolically, it's big P, little a. But when we talk about a Pascal of pressure, that would be 1 Newton of force exerted over a square meter, okay? That is actually a very small amount of pressure. Remember, a Newton is not a large force, so we'll see kind of the consequences of that in a moment. So another thing that we can do is we can measure pressure. The way that I'm going to measure atmospheric pressure today is with a digital gas pressure sensor, okay? It's just this little black box. The way it works is there's an opening to the atmosphere, and again, air particles would be colliding with the sensor part of this, and basically the sensor is a force sensor. It's a membrane that flexes as more or less pressure is exerted on it. So it's doing a calculation for how much force is hitting that membrane and dividing it by the area to give us a pressure. So let me go ahead and bring that value up on the screen. So right now, the pressure here is on the top. It's going to fluctuate a little bit, probably between 101.3 and 101.2, which tells me the actual measurement is probably around 101.25. And it may fluctuate a little bit, so don't worry too much about that fluctuation. But that's measuring atmospheric pressure right now. Interestingly, it's almost exactly equal to what we would call our standard pressure on a typical day. It's usually about 101 kilopascal, so kilo means 1,000, and we take that standard value to be actually 101.3 kilopascals on a typical day at sea level. Now, just to show you that this is actively measuring something, I can take a syringe and attach it to the pressure sensor, and I want to show you that if I compress the air with the syringe, the pressure goes up, and if I pull on the syringe and decrease the pressure, you can actually see that. So I'm going to go ahead and tighten that down, and if I push the plunger, you can see that the kilopascal value goes up, and if I pull the plunger, it actually goes down. So this is actively measuring pressure, and because it's just open to the atmosphere at the moment, it's measuring atmospheric pressure. So there's a place on your notes to note today's atmospheric pressure with a barometer. A barometer is just a pressure sensor that's measuring air pressure. So I would go ahead and record, although it's fluctuating, I would go ahead and record 101.3 kilopascals as our pressure today, okay? And so it is bouncing back and forth a little bit. So today's pressure is roughly 101.3 kilopascals. And again, kilo means 1,000. So that actually is a large amount of force per square meter. It's 101,000 newtons of force per square meter, which seems like a lot, and you might wonder, well, why am I not being crushed under all that pressure? Well, our bodies are adapted to live in that pressure. We've got fluids inside of us that kind of balance that pressure. And I've got a demonstration in another video that shows how if you're able to actually take away that balancing pressure, you can see the very much crushing ability of the atmosphere. It's called a can crusher demonstration. I'll put that link in the notes as well. So we're 101.3, 100.1, or 101.2 kilopascals today. And concept 2 is that pressure acts on all surfaces. What I mean by that is pressure acts downwards, it acts sideways, it acts up. And that has to do with fluid pressure, again, with those particles bouncing around. If my hand is here, they're bouncing into the top of my hand. They're also bouncing into the bottom of my hand and the side of my hand. And I can demonstrate with the gas pressure sensor again in showing that. So let me jump back over to my meter. So the gas pressure sensor is right here. So right now the gas particles are kind of hitting it on the side. If I tilt it up, it still reads 101.3. If I tilt it down, it still reads 101.3. So the gas particles are acting up with the same amount of force as they are when it's sideways, and it does fluctuate a little bit when I move it. But that's an important thing to note too, that fluid pressure is not only going to act on the top surface of something, but also the sides and the bottom. So if you wanted to note some evidence or some support, the barometer orientation doesn't matter. I've got another demonstration where I use atmospheric pressure to force a balloon into a flask. I'll link that in the description as well. The atmospheric pressure pushes a balloon into the flask downwards. It will do it sideways. It will do it upwards. So I'm just going to call that the balloon and flask demonstration. You can check that one out on your own time. Third key concept. Pressure increases with depth. The more fluid there is above an object, the larger the pressure will be. So we don't think of it right now, but we actually live at the bottom of a sea. Okay, it's not a liquid sea, it's a gaseous sea. We've got a lot of atmosphere up above our heads, and gravity is pushing down on that gas atmosphere, and that's what's creating atmospheric pressure at the surface. Some support for this, some things where you might have actually experienced a change in pressure with depth as it regards to air pressure, is if you've flown in an airplane. Our ears are really good pressure sensors. And when you go up in an airplane, you're going up in the atmosphere. There's less weight of the atmosphere above you, and the pressure goes down. So your ears pop, you can feel the pressure change. So traveling in an airplane, or even traveling in a very hilly or mountainous region, when you go up or down a mountain, you can feel that pressure in your ears. So I'll just list that as ear pressure. No pun intended, ear pressure, air pressure. But anyway, one that you might have experienced too, if you're swimming, the deeper you go in a pool, again, you can feel that pressure on your ears as you go deeper. You feel that pressure increase. So I'll put diving in a pool as another example there. And I want to show you a demonstration too where this is definitely viewable. And so let me set it up and then I'll show it to you. I've got a bottle. And what I've done is I've punctured some holes in it. One at the bottom, one kind of further up, and one here. And the idea would be if I would take a pressure, if I would fill this up with water, say, and I take a pressure sensor in here, the pressure sensor I claim would show greater pressure at the bottom than the top, okay? And so I want to show that that actually happens. What happens here with the holes hopefully will demonstrate that for us. So hopefully you can see that. From the top hole, the water is not shooting out as far. The middle hole is shooting out a little bit further, and then the bottom hole has the furthest stream. So if I were to put a pressure sensor over each one of these holes, I would expect the lowest pressure at the top, more pressure at the bottom. So the bottom hole, if I put a force sensor over it, would register the largest force and thus the largest pressure. Because we get the furthest stream here compared to this, that if I were to put a force sensor there, I would measure the biggest force at the bottom of the bottle, okay? So pressure increasing with depth is very important. So I'm not gonna work through the proof of this formula right now, but a physics formula where you can actually calculate the pressure at depth is often written that pressure equals rho, which is a Greek symbol, times G times H, okay? So this is something that you can look up as a proof of this, but basically what it says is the pressure at some depth H will equal the density of the fluid that you're studying, whether that's air or water. This works for gas or liquids, as long as you have roughly uniform density. The density times G is the normal little g that we've used before, acceleration due to gravity, value of 9.8 meters per second, or 9.8 newtons per kilogram. And then you multiply that by the depth. We would want to make sure that our units are worked out the way that we want in our standard units. So we would want our density to be in kilograms per cubic meter. We would want G to be in, say, newtons per kilogram. That's a good version of it here. And then the depth H would need to be in meters. And we would actually be able to calculate a pressure in pascals, okay? So again, I'll leave that for another discussion where that formula comes from. But the deeper you get, the bigger the H, the more pressure you're going to get. So if we are convinced that pressure does increase with depth, this is where we can start to understand the concept of buoyancy, okay? So because pressure increases with depth, the bottom of a submerged object will actually experience a greater pressure and thus force than the top. So the way that could be visualized, if you have some object, it's easiest to think of it in terms of a liquid, but there is a buoyant force with gases as well. It's just smaller. If I were to do some force arrows on this submerged object, and there's going to be a certain amount of pressure acting on the top, because again, we would have liquid particles colliding with that top surface. And then as we go down, as we get deeper, that pressure increases. So here, I'm going to draw the arrow a little bit longer yet, and then longest here. Same on the other side, by the way. So there is pressure on the sides. I try to draw that about the same length. And the pressure on the side just cancels out because it's the same amount at the same depth. But at the bottom, I'm going to have, again, that fairly large force compared to the others acting on the bottom. So when you submerge something in a liquid or fluid in general, because you have more pressure acting on the bottom than the top, you've got a net upward force from the fluid, just for a pressure effect from the fluid. Okay, so one thing that I could say is that the force on the top surface, magnitude, should be less than the force on the bottom. So in other words, you're going to have a net upward force on the object due to pressure in that fluid. Okay, so one way I could calculate that is that force on the bottom is bigger, right? So the force on the bottom, magnitude, minus the force on the top, magnitude, will equal something that we call the buoyant force. So the buoyant force is directly related to pressure increasing with depth. We're going to have a net upward force from the fluid, and usually for convenience, we just consider that to be a single force, a single upward force that we call buoyant force. We know that it's related to pressure increasing with depth, but when we talk about buoyant force, it's just the overall effect of that pressure difference on the object. So if we were to consider a couple of scenarios, do you have a case where you submerge something and the buoyant force, FB, is greater than the pull of gravity on that object? What we have is an upward net force, right? There's an unbalanced force upward, which will result in an acceleration upward, and this thing will float, right? It's gonna accelerate up to the surface and float. If we have the opposite true, if the gravitational force is bigger than the buoyant force, now we have a net force downward, which means the acceleration is going to be downward. And the result there is that the object is going to sink. And we're going to gather some data related to that in just a moment here. In fact, I think I'll put it in a different video. But we want to actually do some quantitative measurements with these different sorts of cases and make some conclusions about buoyant force. All right, so I'm going to go ahead and stop the video now and set up that demonstration, and I will link that video in the description as well.